Isomers. Isomers are molecules that have the same molecular formula but differ somehow in either their arrangement structurally or spatially. So, isomers. So, there are many different ways in which these molecules can differ. So I'm going to go over the different categories and subcategories here to explain to you the different types of isomers that there are. The first kind, and maybe the simplest to understand, is structural. Structural isomers are simply those which have the same molecular formula, but their actual attachment in the bonding, and hence structure, differs. Structural isomers, because of this fact, differ in their melting points, boiling points, chemical properties, reactivity, all of that. They're completely different molecules. They just happen to have the same molecular formula. So let me just use as an example hexane, which has a formula C6H14. Hexane looks like this. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 carbons. Hexane looks like that. So, however, let's just say that maybe we take this methyl group off the end here and stick it on one of these other, carbons instead of having them in a straight line. So this is normal hexane. So let's then take maybe this. So that would be a pentane, and then we took that last methyl group and maybe just stuck it right there. So this is actually going to give us 2 methyl pentane. So that's actually 2 methyl pentane. But let's say maybe we stuck it on one of the other ones. Stuck it right there. Well, that's going to give us 1, 2, 3 methyl pentane. So all of these molecules are completely different in their chemical properties and such. However, they happen to share the same structural formula. Let's just check to be sure. C6H14. So hexane, 1, 2, 3, 4, 5, 6 carbons, and then 14. So we'd have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so that matches. Okay, how about this one? 1, 2, 3, 4, 5 carbons, 6, one up there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, that one matches too. And then 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Again, they all match with the same molecular formula. So we can see that these are in fact isomers of each other. And since they differ in their actual bonding and connections, they are structural isomers. So there's no subsections to structural, it's just that. So the other kind of isomer that we have is a stereoisomer. Stereoisomers have the same molecular formula and they are connected in the same fashion, but they differ spatially. Now there's different ways in which they can differ spatially as well, and I'm going to go over the subcategories right now. The first one would be conformational. So conformational isomers are those which, again, I said they're connected, but they just differ spatially. If you watched video number 5 on Newman projections, what I explained there was conformational isomers. And the way in this is, I'm going to draw a Newman projection down here just to kind of show you. The example I used in that video was butane, so I'm just going to go ahead and draw that one again here. If we have CH3, CH3, H. So this would be butane, and this would be the totally eclipsed conformation of butane. Again, because there's 0 degrees in between these two bulky groups. Like I said, for more explanation on how we get that, please watch video number 5. I go into that. So, and then let's say this one. Okay, and this would be the gauche configuration, in which the two methyl groups are 60 degrees from each other, and here they're 0 degrees from each other. So since this one is totally eclipsed and this one is gauche, these two are said to be conformers of each other, even though they have the same molecular formula. Okay. Another type of stereoisomer is configurational. Okay, is configurational. Now again, here we have two subsections. The first being enantiomers. So, enantiomers. Enantiomers are basically molecules that when you look at them, they're mirror images of each other. So kind of like, you can see my hands right here, how if there was a mirror in between, they're actually mirror images of each other. So that's kind of like a macroscopic view of how we can think of these molecules. Let me just draw an example down here. So mirror images. And I'm going to use a yellow line to represent the mirror in between them. Now this method of drawing here, this is called a Fisher projection, and I'll go into that in my next video, video number 7. How to draw Fisher projections. But this is basically just showing you a molecule. This represents a carbon right here, and these are the 4 things that are attached to that carbon. So as you can see, you know, the 2 chlorines in the center, the methyls on the side, hydrogens on top, and the OHs on the bottom, that these 2 molecules are mirror images of each other, and therefore they are enantiomers. The other type of configurational isomer is called a diastereomer, and basically, you know, if enantiomers are mirror images, diastereomers are not mirror images. So diastereomers are not mirror images of each other. Now, how is this? This, I'm going to draw the example kind of like right here. So see how these ones are a mirror image in every way. Well, a diastereomer is going to have parts of it that are mirror images and parts of it that are not, therefore making it neither conformational nor an enantiomer, but also it cannot differ structurally. So I'll show you how this can be. I'm going to draw another Fisher projection here. And let's just say that we have this molecule, H, OH, OH, CH3, C2H5, and H. So I'm going to draw right here. H, H. So if this was a mirror image of each other, it would look like this. The CH3 would be there, the C2H5 would be there, OH, OH. Now, that's what it would look like if it was a mirror image. However, if we flip all of them, then, you know, if we flip, let's say we flip these 2 across the center here, and these 2 as well. If we flip both of them, then we basically still have mirror images of each other. So the only other way that we can get a different molecule that is neither structurally different nor conformationally different nor a mirror image is to go like this. Now I'm going to erase two of these to show you what to do. And one of them is a mirror image and the other one is not. So the CH3 would be here and the OH would be there. So as you can see, and of course I didn't draw the mirror in between these two because they're not mirror images. In this bottom case here, the C2H5 and the OH are mirror images of each other, but in this top case here, the OH and the CH3 are not mirror images. Now this is how you can tell a diastereomer from an enantiomer. An enantiomer is going to be a perfect mirror image, like the first example that I drew here, before I flipped the top across. So that's an example of diastereomer. Another example, or kind of like one last subcategory of diastereomer, is a geometric isomer. Again, it's still a diastereomer because it's not a mirror image of each other, but it's not as complex as this. So basically this is what we call cis and trans configuration. And this is, you know, this is really kind of like pretty, this is like the easiest one in my opinion to be able to distinguish. How do we do that? Is, for example, let me just take so cis and trans specifically applies to alkenes, so double bonds. So let's say we have a carbon double bonded right there, and let's say we have a hydrogen there, methyl group there, and another hydrogen here. And then over here I'm going to draw another very similar molecule where we have a hydrogen there, a hydrogen there. Okay, so in this case, let's just count to make sure that we have the same molecular formula. 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons, and 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So this is butane, 2-butene actually. This is 2-butene. They have the same molecular formula. However, as you can see in their arrangement, this bulky methyl group right here and right here and right here and right here, we can see that in this one they are on opposite sides of the molecule, whereas this one they're on the same side. So basically if they're on the same side, we just call it cis, and if they're on opposite side we just call it trans. So since I said that this was 2-butene, 1, 2, 3, 4 butene, on the second carbon is the double bond, so 2-butene. So this would just be trans 2-butene, and this one is cis 2-butene. So that's it. And that's basically all of the isomers that there are. So for more in-depth explanation of how to draw Fisher projections, that'll be my next video. So thank you.